Hello, my name is Anthony Kennedy, and this is my Lab 5 on magnetic braking. The purpose of this lab was to use the aluminum foil, a magnet, and a phone to create an experiment to test the idea of magnetic braking by timing the magnet's exit from the aluminum tube. A quick preview of my results, you can see here that just dropping the magnet through space without any sort of apparatus, I get around 0.2236 seconds. This is just what my phone told me. Experimental, this is when I drop my magnet through the actual tube. I got 1.14 seconds. In my computational model, I got 1.244 seconds. Next slide. The procedure I went about doing this experiment with is first I held the camera a distance from the tube. I didn't have three hands, so I just kind of put it up on a thing. And I had the camera just running. And, I'm just going to assure the camera shows the exact time. I hold the magnet above the aluminum tube, which is suspended in the air, so there's no conduction anywhere else. And then I simply drop the magnet through the tube. I go to my phone. I discover the time taken. I kind of look when the magnet enters and when it exits. And then I use the timing, like the time in between the entrance and the exit, to determine how long it took to fall through the tube. A few of the important fundamental principles for this lab, what I would have to say is magnetic dipoles. Well, that's what this magnet is. And almost to another extent, with the current induced, the ring of current is a magnetic dipole. So there's a lot of dipoles just going around this idea in general. You have Newton's first and third laws, which inform the position and velocity update formulas, which you use in the computational model so that we can, computationally derive how fast and where the magnet is, so we can use that to derive how fast it is, and so on and so forth. Faraday's law, that's important because that's the law that informs why the magnet induces this EMF in this aluminum foil, so that it produces the current that runs opposing to that produces the current that produces the field that goes on to produce the force on the magnet. This is kind of Lenz's law, right? That slows down the magnet, kind of goes opposed to the downwards force of gravity, which is why it's so drastically slower. Even in both the computational and experimental, it's almost like a factor of 5 slower than how gravity would just normally put it when it's just in the air. Few of the specifics to my coding: I have the tube length at 0.2 meters, the foil width at 0.02 meters, the inner radius, the radius inside the foil, you understand, 0.015 meters, and the mass of my magnet was 0.024 kilograms. And this is just, my previous result for the computational model, 1.244 seconds. Here's a little bit of the specifics of my coding. Here you can see how I got the magnetic field on the ring, how I put in the sine theta, the functions I used, and how I got the net force magnetic. You can see it's only in the y direction. That's important because of the direction of the magnet falling, the direction of the flux. It's in the n hat vector, and that's going to be just straight in the y direction. So of course the force magnetic is going to be induced in the same way as well. So that's the same direction as the change in flux. And then you also see here how I utilize the position update formulas with the delta t given by the coding to update my position and therefore update the rest of the coding so I get in as accurate as possible as I could get from the computer. You can see here my graph. It's a little odd shaped, but that can be explained by the fact that, nature wants to find equilibrium. So the velocity is going negative faster. It hits the tube. As it goes faster, it gives a more reversing magnetic force, so it hits this equilibrium as it's falling through the tube in this 1 second. And then towards the end, as it's exiting the tube, of course gravity starts to take the initiative again and it falls through faster. A few of the possible sources of error: you can definitely say inaccurate timing due to the phone, due to human error. To be fair, I was pausing around exactly when I thought it left the actual tube. That's likely not exact. And also non-exact measurements, I didn't have a laser measure. I used the tape measure like everybody else. Further discussion: what if the resistivity of the conductor was reduced to 0? The magnetic force would likely increase to the point where it counteracts the force of gravity, entirely removing acceleration. That's not to say it wouldn't be falling, as it has some momentum likely, but yeah. And if you decided to cut a bunch of holes in your tube, which all right, The flow of the current would be interrupted because it's just holes in your loop, and there's less current, which means less magnetic field, which means less magnetic force, and thus you get a slower fall. Thank you for listening to my presentation.